today we are going to talk about something called the conservation of momentum. A reminder that momentum is a quantity of motion. So if you're describing the motion of some object in terms of numbers, you are describing its momentum. And momentum is a vector, and that point will become very, very important in this lesson. So make sure you remember that momentum always includes not only a magnitude, but also a direction. Before we get started, I wanted to give you a little preview for what your homework is going to be tonight. You have these three problems. During a safety crash test, a 1,500 kilogram car is crashed into a wall at 60 meters per second. What is the car's initial momentum, and what is its final momentum? If it takes the car 0.7 seconds to come to a stop, what force does the crash test dummy feel? Do you think a human would survive this crash? And finally, explain how this collision obeys the law of conservation of momentum. So, the first two problems are a recap of the last two videos that we've gone over, and the third one is from this video. So, conservation of momentum. I'm sure most of you have already guessed that it is like all other conservation laws in that something is conserved, meaning it's the same before as it is after. So during any collision, measurements show that the total momentum of the system does not change. Total momentum means the momentum of every object in that collision added together. So if we have ball A and ball B, we'll say they're billiard balls or pool balls, and they're coming at each other and they're going to collide. A has a certain amount of momentum based on its mass and velocity, and B has a certain amount of momentum based on its mass and velocity. And when we add those together, we get a total momentum for before the collision. After they collide, ball A has some new momentum based on its mass and velocity after the collision, and the same with B. And when we add these together, we get a momentum total for after the collision. And the law of conservation of energy tells us that the total momentum before and the total momentum after are equal. It does not matter how these things collide. That statement is always true. The only time momentum is not conserved is when there is an outside force acting on an object within that system. So it turns out if you zoom out far enough in terms of your reference frame, this law holds true. But if you are too zoomed in on your reference frame such that there is an external force that is not accounted for acting on your objects, the law of conservation of momentum will seem like it does not apply. That is really important to keep in mind when thinking about how to answer number 3 on your homework. So the definition, the textbook definition of the law of conservation of momentum says the total momentum of an isolated system of objects remains constant. And this is what I was talking about when I mentioned your reference frame or your point of view. So as an example, if we have these trolley cars and B is at rest and A comes and crashes into it, the momentum of this whole system before the collision has to be the same as the momentum of this whole system after. In this case, our isolated system is only trolley car A and trolley car B. We are ignoring everything else. We're ignoring the rails and the friction that presents. We're ignoring air resistance. We're ignoring every single thing else other than these two trolley cars. So when you talk about momentum, you need to be really specific about what your system is, what the objects are. So, like I said before, momentum is conserved in all collisions, and this is super, super important. No matter how things collide, momentum is always conserved. However, when we have kinetic energy conserved in a collision, that is something called an elastic collision. And when kinetic energy is not conserved in a collision, that is an inelastic collision. So no matter how things collide, momentum is always conserved. But kinetic energy may or may not be conserved. So what does it mean for kinetic energy to be conserved? Well, for something to be conserved, that means the kinetic energy before the collision must be equal to the kinetic energy after the collision. And hopefully you all remember off the top of your heads the equation for kinetic energy, because we just did it. 1/2 mass times velocity squared, don't forget the squared, of the system before has to be equal to 1/2 mass times velocity squared of the system after. So when momentum is conserved, mass times velocity before equals mass times velocity after. But if kinetic energy is conserved, that means 1/2 mv squared before is equal to 1/2 mv squared after. And we are going to talk a lot more about the difference between elastic collisions and inelastic collisions. But I just wanted to throw this out there to give you a little bit of a heads up. So what I want you to take away from this right now, kinetic energy is not always conserved, but sometimes it is. But momentum is always conserved. So there's a little disclaimer here. The majority of all collisions are inelastic, meaning we lose a little bit of kinetic energy in some other form of energy. And if you think about it, that could be heat energy, thermal, from friction. It could be sound energy. It could be light energy if there's a little explosion. An example of a collision that is totally elastic, meaning kinetic energy is conserved, is a collision between gas molecules. What we're going to do for the purposes of this class is pretend everything acts like gas molecules do. When they collide, we are going to assume that it is an elastic collision unless you are explicitly told this is inelastic or the objects stick together. When the objects stick together after they collide, that is an inelastic collision for us. When the objects do not stick together after they collide, that is an elastic collision. So let's go ahead and use a little applet for a second to try and get a feel for what elastic and inelastic collisions look like. This applet is really meant to show that the momentum before a collision is equal to the momentum after. So we will have the momentum shown. You can see momentum for wagon 1 and wagon 2 up at the top. And right now, I have this set to an elastic collision, and that means when one cart comes in, it is going to bounce off the other. So let's go ahead and run this for a second. So through that, you could see the blue cart was stopped and the red cart was moving. And when the red cart hit the blue one, the red one stopped and transferred all of its kinetic energy to the blue car, and the blue cart moved away. We can also set this to an inelastic collision, which means the two carts are going to hook together. So the blue cart is not moving, and the red cart is coming in to hit it, but they're going to stick together when they collide and move together as one thing. So the total momentum now is the same as it was before, but instead of all of that momentum coming from one object to another, it is distributed across both of those carts because they are now a single object, and we've lost some kinetic energy there. So when things stick together like this, kinetic energy is lost, and when they don't stick together, kinetic energy is conserved. Hopefully that is making a little bit of sense. So the conservation of momentum comes with some equations that you need to know how to use to be able to apply to a problem. So the conservation of momentum tells us that the momentum before a collision is equal to the momentum after the collision. So what we can do is go ahead and put in our equation for momentum and plug that into these parts right here. Well, I'll make the top one in a different color. There we go. So momentum before a collision is the momentum of both of your objects, or if you have 3 or more, all of those objects combined. So object 1 will have its own momentum, mass times velocity, and object 2 will have its own momentum, its mass times its velocity. But in order to get the total momentum before the collision, you need to add those together. It's the same for after the collision. Now, object 1 has its own new momentum, and object 2 has its own new momentum. But in order to get the total momentum after the collision, you need to add them together. And what do these little symbols mean? Well, the little symbols up at the top here are called primes. So you would read this m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And the prime means final. So anytime you see, it's almost like an apostrophe. Anytime you see that little apostrophe up there, that means it is the final velocity. It is the velocity after the collision has happened. So let's try and apply this to a problem. There are 2 ice skaters, one with a mass of 60 kilograms and the other with a mass of 75 kilograms, and they are facing each other initially at rest. So we have an ice skater here and an ice skater here, and they are facing each other at rest. I'll give them some ice skates. They kind of look like skis. So they push off each other, and the 60-kilogram skater moves backwards at 5 meters per second. How fast and in what direction does the 75-kilogram skater move? So we are trying to find out what is his final velocity, or hers, whatever they are. So we need to start with the law of conservation of momentum. It turns out, even though this isn't a collision in the way that we think of them as 2 things smacking together, this is in fact a collision. It is an interaction of 2 objects. So we need to apply the conservation of momentum, because no matter what, momentum is always conserved. And that means the momentum before the collision, or before they push off, is equal to the momentum after the collision, or after they push off. So m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. So let's go ahead and list everything that this problem gives us. We have 2 ice skaters. The mass of the first one is 60 kilograms, and the mass of the second one is 75 kilograms. And they are both initially at rest. So that means V1, initial velocity for skater 1 is 0 meters per second, and the initial velocity for skater 2 is 0 meters per second. After they push off from each other, the 60-kilogram skater, or skater 1, moves backwards at 5 meters per second. So now that is skater 1's final velocity, or V1 prime. And that is 5 meters per second. And we want to know skater number 2's final velocity. That is what we're trying to find. So now we have everything. All we got to do is plug it into our equation for the law of conservation of energy and solve. So m1v1 plus m2v2. m1 is 60 kilograms, v1 is 0, plus m2 is 75 kilograms, v2 is 0, and that is equal to m1 is still 60 kilograms, and v1 prime, or that skater's final velocity, is 5 meters per second. m2 is still 75 kilograms, and we do not know the final velocity of this skater. That's what we're trying to find. So everything on the left-hand side of the equation goes to 0, because we have 60 times 0 plus 75 times 0. And we are left with 60 times 5 is 300 kilogram meters per second, plus 75 times v2 prime. Subtract 300 from both sides, so we have negative 300 kilogram meters per second is equal to 75 times v2 prime. And now to solve for this velocity, we have to divide both sides by 75. And when you do that, you find that v2 prime second skater's final velocity is 4 meters per second in the negative direction. So we know that it's moving at negative 4 meters per second, but what direction is that exactly? Well, we called the 5 meters per second of the first skater positive, and that was to the east. So if the second skater is moving in a negative direction, that must be the opposite of east, which is west. So the final answer for this problem is v2 prime equals 4 meters per second west. And that's your answer. So now that we have done this sample problem together, go ahead back to the homework problems, here they are, and answer these to the best of your ability. Remember, you will have to apply things you've learned in the previous 2 videos in order to answer these questions.